So these are my disclosures, and this is the outline of my presentation. So I'm going to discuss with you why we need seizure detection using wearable devices. How do we know they really work? I will show you validated devices, and I will tell you about the relatively recently published guideline about wearables for seizure detection issued by the ILAE in collaboration with the International Federation of Clinical Neurophysiology, IFCN. And because it's 4 years since we published this guideline, I will show you also some more recent literature update. And I will tell you about ongoing research in development and also some future perspectives. So, why do we need automated seizure detection? Well, we need that for intervention and prevention because seizures lead to injuries, and the generalized tonic-clonic seizures, including the focal to bilateral tonic-clonic seizures, are the major risk factors for SUDEP. We would need this for closed-loop systems so that an automated seizure detection would trigger an on-demand therapy. The unpredictable nature of seizure occurrence is distressing and disabling, both for the patients but also for the caregivers. And this leads to social isolation and, of course, decreased quality of life. Roughly half of the seizures remain unrecognized by the patients. So we could say that the therapeutic decisions, but also the drug trials, are based on unreliable data. And of course, the unreported seizures are mainly the nocturnal one, 85%, but also almost 1/3 of the seizures occurring during the daytime remain unrecognized by the patient. And of course, this is mainly the focal seizures with impaired consciousness, that's 73%, but also almost half of the secondarily generalized or focal to bilateral tonic-clonic seizures remain unrecognized by the patients. And of course, we know from large patient survey studies that there is a need for wearable seizure monitoring. Both the patients, the caregivers, and also the healthcare personnel said in these surveys that they definitely need a reliable automated seizure detection. There are lots of papers about seizure detection. If we restrict that to wearables and seizure detection, almost 300 papers. But can we trust them? Do they really work? What is the level of evidence for these devices? Well, together with my friend Philippe Rivlin, we suggested standards for testing and clinical validation of seizure detection devices. We identified 4 key features: the subjects, recordings, the analysis and alarms, and the reference standard. And for each key feature, we indicated how to decrease the potential bias. So for example, when it comes to the subjects, of course, you can start by playing with simulated data or a low number of patients. But of course, the real thing is to analyze data from real patients, and a larger number, a high number, is better than a lower number. That's just common sense. And of course, when it comes to the recording, you can start playing with conventional methods, but the real validation is by using the dedicated wearable device itself. Continuous is better than discontinuous, multi-center is better than single center, prospective is better than retrospective, nothing special about this. Now, when it comes to the alarms and analysis, of course, you can start by training and testing the algorithm using the same data set, but the real validation is when you use predefined algorithm and a predefined cutoff value. Of course, you can start by playing with the data and then analyzing them offline retrospectively. But the real validation is when you run the algorithm real time and you get a real-time alarm and seizure detection. Of course, blinded is better than not blinded, and definitely you need a reference standard, a robust gold standard. And the best for this is the video EEG recordings, but for major motor seizures, you can rely also on the video as gold standard. Now, we took these key features and these aspects of the study design, and we tried to set up the 5 phases similarly to the drug trials, to the therapeutic trials. So in this case, phase 3 provides you the compelling evidence that the device actually is reliable, is accurate. What do we need for a phase 3 validation study? Of course, you need real patients with real seizures. And these numbers you can see here, so 20 patients, 30 seizures, they are for the devices with a sensitivity over 95%. The lower the sensitivity, the higher number of patients you need to recruit to these studies. Of course, you must do the validation study using the dedicated wearable device. You must have continuous recording. You must do it in a multi-center design. You must have a predefined algorithm and predefined cutoff values. You must run the analysis real-time, blinded, and you must have a clear gold standard from video or video EEG. Now, phase 4 would be equivalent to an open label in-field study showing the clinical utility. But the phase 3 is what would correspond to a randomized controlled trial in drug trials. So we used these principles when we evaluated the literature, when we developed the ILA IFCN guidelines 4 years ago. The working group was appointed by both societies, and we followed the ILA's methodology for guideline development. That is, we used the PRISMA standard for the evaluation of the published literature, and then we weighed this using the GRADE standards. The proposed guideline was out there for public hearing for more than 2 months on the homepage of the ILA. And very importantly, this was also reviewed by the patients' organization, by the International Bureau for Epilepsy. In the end, the guideline was endorsed by both societies. So here you can see the PRISMA flowchart. This is now a little bit outdated because we searched the literature until October 19, and we found altogether 28 studies which qualified for phase 2, 3, and 4. But since then, we also updated the literature search. So this is a recently published systematic review after the guideline. Well, spoiler alert, even after the update of the systematic literature search, the conclusions in the guideline would not change. So when we did the literature search for the guideline, we found that there was reliable evidence for seizure detection using wearables for the major convulsive seizures, that is the generalized tonic-clonic seizures, including the focal to bilateral tonic-clonic seizures. So when we did the guideline, we found 3 studies which qualified as phase 3. Since then, 3 more were published, but again, that would not change the conclusions in the guideline. And then when we published the guideline, we found 2 studies which qualified for phase 4. 3 more were published since then, but again, that would not change the conclusion in the guideline. So the sensitivity of the wearable devices for catching the generalized tonic-clonic seizures is between 90 and 100%, so this is really good. However, the false alarm rate is between 0.05 and 0.7 during 1 day. Now, the good news is that during the night, the false alarm rate is really, really low. So 1 false alarm in 300 nights in some studies, and no false alarm during the night at all in studies using multiple modalities. So this is good because during the daytime, the patient or the caregiver simply can cancel the false alarm. But of course, during the night, the false alarms are really annoying, but that's rare, or even for some devices, that's zero. Now, for the other seizure types, we call them non-convulsive. When we did the guideline, we only found phase 2 studies, and then since the guideline, one phase 3 study was published concerning automated detection of the absence seizures, and there is one more phase 3 study which is currently under review. Now, many devices achieve a sensitivity over 90% also for the non-convulsive seizures. However, the problem with these seizure types and these gadgets is that the false alarm rate is really, really high, still high. So for some of these devices, up to 500 per day, which kind of precludes their clinical implementation. However, we have promising results with wearable subcutaneous EEG. Now, let me show you the validated devices for detecting generalized tonic-clonic seizure. So here you can see a bracelet with an accelerometer, and here in the 3 colors, you can see the accelerometry signals in the 3 dimensions of the space, and this is a generalized tonic-clonic seizure. Now, there is a Bluetooth connection between the wearable device and a smartphone, and the smartphone has also GPS, so can alert even if the patient is outside the home. This has been validated in a phase 3 study, of course, multi-center, prospective, blinded, real-time analysis, predefined cutoff values, and the algorithm. Altogether, 73 patients were recruited, 39 generalized tonic-clonic seizures from 20 patients, gold standard from the epilepsy monitoring unit. The sensitivity of this accelerometry-based unimodal device was 90%. However, the mean detection latency was a little bit too long, was 55 seconds. Why? Because the accelerometry is mainly active during the clonic phase of the tonic-clonic seizure, so per definition, that comes later during the seizure. Now, with this device, the false alarm rate was 0.2 per day. Then we started playing with the surface electromyography, and I don't know whether you include surface EMG in your electrode array when you monitor patients with epilepsy, but it gives you a really nice signal. It's almost like an archetype of the generalized tonic-clonic seizure. You can see here at the bottom of the page in green, that's the EMG signal from a generalized tonic-clonic seizure. So we looked at it quantitatively, and we found that the energy is increasing in the high frequency domains. And here you can see that the amplitude is increasing and there is a peak in the frequency. So we designed a biomarker for generalized tonic-clonic seizures, and then we built our seizure detection model on this biomarker. Here you can see that we filter with a really high value of the high pass filter with 150 Hertz because we want to catch the high frequencies, and then we count the number of zero crossings because we want to go for the high frequencies. So here you can see the surface EMG signals recorded with this mini surface EMG wearable device. And we validated this also in a phase 3 clinical study. We found a sensitivity of 94%, much shorter detection latency, only 9 seconds. And this is because this algorithm is activated already during the tonic phase of a tonic-clonic seizure. The false alarm rate was 0.7 per 24 hours. Fortunately, during the night, the false alarm rate was really, really low, so only 1 false alarm in 100 nights. Now, we trained using machine learning an algorithm to find those generalized tonic-clonic seizures which are dangerous, which have a long post-ictal generalized EEG suppression, because those indicate a higher risk for SUDEP. And this machine learning-based algorithm detected these dangerous generalized tonic-clonic seizures with long post-ictal generalized EEG suppression with an accuracy of 85%. We use this algorithm also to distinguish between the generalized epileptic, generalized tonic-clonic seizures, and the convulsive non-epileptic psychogenic seizures. And the algorithm distinguished between these two categories with an accuracy of 95%. And probably you've also experienced this in many emergency rooms. There are no epileptologists, so often these patients with convulsive psychogenic non-epileptic seizures are aggressively treated because they are misdiagnosed as having convulsive status. Now, this is another device. Here you can see this is a multimodal device. It has both accelerometry and heart rate built in it. And this was validated in a combined phase 3 and 4 study by our Dutch colleagues. Again, it was multi-center, prospective, blinded, real-time analysis. The problem with this study is that although all seizures were new in the validation phase, half of the patients participating in the validation phase previously gave their seizure data for training the model. So yeah, you could say the seizures were new, but not all the patients. And then there was some other issues with the quality of the gold standard. So all videos were analyzed by a nurse, and only selected video segments were analyzed by epileptologist physicians. Anyway, the overall sensitivity for catching the generalized tonic-clonic seizures was 81%, and the device could also detect other major motor seizure types with a sensitivity of 77%. The false alarm rate was relatively low, only 0.03 per night. This is another multimodal wearable device by Embrace. It combines accelerometry with electrodermal activity. This was validated in probably the largest phase 3 clinical trial for wearable devices for seizure detection. 152 patients were recruited, and 36 patients had generalized tonic-clonic seizures. They also had a robust and reliable gold standard from the epilepsy monitoring unit. Very good sensitivity, 98%. Relatively low false alarm rate, 0.84 per 24 hours. Very importantly, zero false alarm during the rest period, zero false alarms during the night. The median detection latency was 37 seconds. This is a little bit long because the algorithm mainly relies on the accelerometry signals. And you remember, accelerometry is mainly activated during the clonic phase of the tonic-clonic seizure. Now, this study was also published after the guideline. It's on Apple Watch. So there's a huge potential in this because Apple Watch is really widespread and available. And the colleagues from Baltimore trained this algorithm on Apple Watch and then validated it in a phase 3 clinical trials. 85 patients were recruited in the epilepsy monitoring unit, and they also had an ambulatory arm with 13 patients. Now, the sensitivity was 100%, so this algorithm detected all generalized tonic-clonic seizures, of course, including focal to bilateral tonic-clonic seizures. The false alarm rate was 0.05 in the epilepsy monitoring unit and 0.13 per day at home, which is still really, really good. The median detection latency is 32 seconds to 37 seconds. Again, a little bit long, but this is also based on the accelerometry signals combined with PPG. So the heart rate is calculated from photoplethysmography from this watch. Now, this is another modality. This is even less intrusive. This is just video. So we played with the automated analysis of video using artificial intelligence. Now, let me show you how the computer vision works. So can you see all these small arrows? So this is what the algorithm senses. So all the tiny movements can be detected. So even a pulsating artery can be detected by the algorithm. Now, we validated this in phase 3 clinical study, and it seems it only works for the major convulsive seizures. So we detected all the generalized tonic-clonic seizures, and 4 out of the 5 hypermotor seizures we had during this study period. It wasn't very convincing for the minor motor seizure types. And unfortunately, even like this, the false alarm rate was really, really high. So it was 0.16 per hour. So that means that you would get almost 4 false alarms per day. So this could be used for institutions where you have a nurse during the night shift, and this could help the nurse to detect the seizures and survey more patients. But of course, at this rate of false alarms, this is not usable at home. Now, our Swedish colleagues use it for another use case scenario, for another indication, for detecting and analyzing nocturnal seizures in the home environment of the patients. This is semi-automated. So during the night, the algorithm runs and marks epochs where there is a high risk for seizure, and then an expert has to review these spots. The good thing about it is that it reduces the data, so you don't have to sit there and watch the video of 8 hours sleep, but you have to go for these spots marked by the algorithm. And this way, our Swedish colleagues found a diagnostic yield of 55%. For the major focal seizures, this was 82%. This is in what percentage they could catch the nocturnal seizure by this method. And then the clinical utility, where they could also diagnose it, was 40% in the entire cohort. And for the major focal seizures, this was 64%. Now, all these are phase 3 validation studies. How about phase 4? What do we know about the clinical utility? Well, we addressed that in a study where we followed up patients who wore the bracelet, the unimodal accelerometry-based system. And you can see that there was a very high retention rate. So less than 10% of the patients stopped using the device for a reason related to the device itself. And on this 7-point Likert scale, the median was 5.5. So the users, the patients, and the caregivers were really satisfied with this wearable device. The median usage time was really long, 15 months. And the performance reported in field, that is mainly generalized tonic-clonic seizures validated by the caregivers and the family, that was almost identical with what we found as performance in the epilepsy monitoring unit. So that's good news, because probably we can extrapolate these data from the epilepsy monitoring unit to the real home environment of the patients. But the most important finding in this phase 4 validation study was that the patients and caregivers said that the alarm helped them to log seizures in their seizure diary in 55% of the cases. And they also said that the alarm helped them to prevent injuries in 40% of the cases. Now, this is a very nice crossover design for a phase 4 validation study with the night watch. They looked both at the stress level and the quality of life of the caregivers, of the parents of the children wearing these devices. Again, the performance in this home environment was similar to what they previously found in the phase 3 clinical validation study. The caregivers' stress level indeed decreased significantly. However, they were not able to find significantly improved quality of life. I think this is partly due to the relatively high number of false alarms in this study. Then we also did a survey study with the real-world experience. So we asked patients who actually used wearable devices for seizure detection in their home environment. Most of these patients, most of the 242 patients had generalized tonic-clonic seizure, but it's good because that's the seizure type which can be reliably detected at the current state of art by these devices. The median usage time was also long, 14 months. Overall, there was a high level of satisfaction on the Likert scale. And here in this Kaplan-Meier curve, you can see that the retention rate was higher for those devices which were actually validated in phase 3 studies as compared to the other devices. Again, very importantly, in 65% of the cases, the users said that the alarm helped them to log the seizures into the seizure diary. And in 30% of the cases, the patients and caregivers reported that the alarm helped them to prevent injuries. Okay, so could this help prevent SUDEP? Of course, it's very difficult or almost impossible doing a prospective randomized study on this. However, we can infer indirect evidence because we know from large population-based Swedish studies that 91% of these patients die at home, 71% are living alone, 65% are found in bed, and 82% in a prone position. So patients without nocturnal surveillance, not sharing a bedroom, and experiencing tonic-clonic seizures have a 67-fold increase in risk of SUDEP. So again, we don't have direct evidence, but I think we have a strong indirect evidence indicating that if there was seizure detection and an alarm came and an intervention came in time, then we could prevent these SUDEP cases. However, it's very, very important to emphasize linking the alarm with the intervention in a short time. And this is sadly shown by the case of a 20-year-old patient who wore a risk sensor. This was the Embrace device, which detected accurately the generalized tonic-clonic seizure at 8:50. And a caregiver trained in cardiopulmonary resuscitation arrived 15 minutes later, found the patient pulseless, prone, facing pillow with mucus. He performed CPR for 15 minutes without success. So again, if the help arrives 15 minutes later, that's too late. Okay, how to detect non-motor seizures using non-invasive wearable devices. Of course, you can detect the non-convulsive seizures using EEG. However, the patients do not want to wear 64 or 25 electrodes all the day, so they want to avoid stigma. Of course, you can hide these electrodes by implanting them. Patients accept that if that's linked to an intervention, to a therapy, but not just for seizure detection. So we played with EKG, with electrocardiogram data, because 82% of the patients experiencing seizures have also heart rate changes, mainly tachycardia related to the seizure. And it's very easy to record EKG. You just put 2 electrodes on the body and then you have the EKG. Now, we played with several measures, but then we found that the best is the so-called modified cardiac sympathetic index. So this is a heart rate variability measure where you plot one RR peak against the next RR peak. And here you can see that you can calculate the longitudinal and the transversal dimension. And here you can see how this changes during a seizure as compared to how it changes during an exercise. So you can see that the longitudinal aspect is much more prolonged. So we took the square of it, so that's why it's the modified cardiac sympathetic index. Why is this important? Because if you just trigger the alarm based on tachycardia, then you would have a very high false alarm rate. So now we tried to distinguish between the ictal heart rate changes and the physiological heart rate changes, and it seems that the modified cardiac sympathetic index does that. So here you can see how the modified cardiac sympathetic index steeply increases just during the seizure. So the seizure is here marked in red. However, during a normal physiological exercise, so we put the patients on the exercise bike, there is no peak. So we constructed an algorithm and we ran the algorithm in this wearable mini EKG device. We had two previously published phase 2 studies on this topic. Roughly half of the patients are responders. So obviously, this method wouldn't work in all patients. It only would work in those patients who have a significant or marked autonomic change during the seizure. Now, in our series, this was a little bit higher than half of the patients. And the sensitivity in the independent test data set was 81% for the non-convulsive seizures and 90% for the generalized tonic-clonic seizures. Then we improved the algorithm, and then we ran it in a prospective study with phase 3 design. And the sensitivity overall was 90%. It detected all focal to bilateral tonic-clonic seizures, and the other focal seizures were detected with a sensitivity of 82%. Now, the false alarm rate was roughly 1 per hour, but this was median 0 during the night. And during the day, the caregivers and the patients canceled successfully the alarm. So with the patient's intervention, we could also compensate for these false alarms. Now, in a pilot study, we implemented this heart rate variability-based algorithm on a subcutaneously implanted EKG. And I think that would be the future of EKG-based seizure detection, because the patients do not need then to change the plaster every day. It's implanted there. So in this pilot study, we found a sensitivity of 92% with a false alarm rate of 2.7 per day. Where else could you hide EEG electrodes? Well, you could use ear EEG electrodes. Some pilot studies showed promising results, but only for generalized tonic-clonic seizures. And actually, if you look at the data, the detection is based on EMG artifacts recorded by the ear EEG electrodes. This is the behind the ear EEG. Here you can see the electrodes. This was again in a phase 1 and then later on a phase 2 study investigated. The sensitivity was around 63% and the false alarm rate was 0.8 per 24 hours. And recently, we played with the subcutaneously implanted EEG electrodes. So here you have 3 channels, 3 electrodes, which gives you 3 channels, and we found promising results. Here you can see the device, which is implanted under the skin. So it's a subcutaneous electrode. And then we had a semi-automated approach. First, we scan the EEG with an algorithm, and then an expert looks at these signals. We've recently published a study about its clinical utility. So here you can see the gold standard from the epilepsy monitoring unit, the beautiful seizure in the epilepsy monitoring unit. Here you can see the seizure detected with the subcutaneously implanted EEG. Here you can see the beautiful seizure fingerprint, the so-called chirp. So these are really, really useful. And this is also targeted by the algorithm, but then an expert reviews this. So we found that these were reliable in 3 out of 5 patients, and it had an added value in 4 out of 5 patients. Now, this is another phase 3 study on non-convulsive seizures. This is on absences, and the use case scenario is to monitor the therapeutic effect. So the concept is that after the medication, the patients would record half an hour each day at home to see whether the absences have decreased or disappeared. Now, in this phase 3 clinical validation study, we found a sensitivity of around 80%. The median per patient was over 90%. The false alarm rate was 0.6 per hour, and the F1 score was 0.75. So, coming back to the ILA IFCN clinical guideline. So, we used the grade to weigh the published evidence. Concerning the detection accuracy, we found high level of evidence for the generalized tonic-clonic seizures, but for the non-convulsive seizures, the evidence was only moderate. Concerning the balance between desirable and undesirable effects, that is, do these desirable effects, such as seizure detection, outweigh undesirable effects, such as the false alarms or the burden of usage? Well, we found evidence only for generalized tonic-clonic seizures, and this was very uncertain for the non-convulsive seizures. Concerning the values and preferences, it was easy because everybody would like to have these gadgets. But concerning the wise use of the resources, in other words, does currently available automated seizure detection provide input for meaningful outcome, that is prevention of injuries, prevention of SUDEP, objective seizure quantification, or increasing quality of life? Well, this was uncertain even for the generalized tonic-clonic seizures, and we found absolutely no evidence for the non-convulsive seizures. So based on this, the recommendation issued by the ILA IFCN sounds like this. So we recommend using clinically validated wearable devices for automated detection of generalized tonic-clonic seizures, including focal to bilateral tonic-clonic seizures, when significant safety concerns exist, especially in unsupervised patients who do not share a bedroom, but alarms can result in a rapid intervention within 5 minutes. So you see, lots of ifs. So if alone and if the help can arrive soon. And at present, we could not recommend the use of these devices for other seizure types. There is definitely need for further research and development to increase the performance of wearable devices and algorithms, especially for the non-convulsive seizures, to decrease the false alarm rate, even if that's done offline, which would allow an objective documentation of seizure frequency, to conduct properly designed clinical validation studies. And we definitely need phase 4 studies, in-field studies, to demonstrate whether automated seizure detection leads to meaningful clinical outcomes such as decreased morbidity and mortality associated with seizures, objective seizure quantification, or improved quality of life. So, to sum this up, there is evidence that the wearable devices accurately can detect generalized tonic-clonic seizures, including focal to bilateral tonic-clonic seizures. So we know this from phase 3 validation studies using unimodal accelerometry or surface electromyography or multimodal devices combining accelerometry with heart rate or accelerometry with electrodermal activity or PPG. And we also have phase 3 studies on the automated video analysis using artificial intelligence. And there are promising results also for the non-convulsive seizures. So we have phase 2 validation studies with subcutaneous EEG and EKG. And then we have phase 3 validation studies. One was published for the absences with a one-channel EEG. And then we have for the focal seizures, focal non-convulsive seizures, we have a study which is currently under review using heart rate variability with surface EKG. Everything else is still in development. And at the end of the lecture, I would like to flash up the aerial view of my two affiliations. So this is Aarhus University Hospital, which is actually the largest hospital in Scandinavia. And this is the Danish Epilepsy Center, which is really a nice and cozy place in the forest. And if you are interested in learning more about mobile health and digital technology in epilepsy, I would like to invite you to attend the 5th International Congress, which we are organizing in Copenhagen. And this is just after the International Epilepsy Congress in Lisbon in Portugal. So if you take the transatlantic flight, stay a couple of more days in Europe and attend the Congress also in Copenhagen. Thank you for your attention.
Thank you so much, Dr. Beniczky. That was really a wonderful overview of the current state of seizure detection devices and where we're going. Very exciting. I'll just get you to unshare your slide if you don't mind.
Yeah, sure.
Panelists. And Dr. Lisa Lomax is going to go through some of the questions from the chat and moderate the Q&A.
Yeah, thank you again, Dr. Beniczky, for this fantastic talk. Very interesting. The first question in the chat is, can